Section 1.8, the power of a product and quotient. Should be very similar. Like, I don't think it's going to be a big leap at all coming out of like the last couple sections. I think we're only going to kind of maybe make things ever so slightly more complicated. So it really shouldn't be a difficult leap to make to kind of move on to section 1.8. So let's see what we're getting into. First of all, remember from before, from basically last section, that if you raise, where's my cursor? There it is. If you raise a power to a power, because of all this stuff happening, you know, behind the scenes, you end up really just, at the end of the day, multiplying the powers together for, you know, to simplify it. Today we're looking at this, like I said, like a little bit more complicated. So what does it mean to raise this bubble, or anything, to the third power? Well, doesn't it mean like this bubble of stuff multiplied by itself 3 times? You know what I mean? And then, you know, to kind of keep breaking it down, right, and expanding it, and then putting like the 2 times the 2 times the 2, and then all of these x's multiplied together, and then all of these y's multiplied together. You end up getting 8. That was the 2 times 2 times 2. And then, or like, in other words, 2 to the third power. And then all the x's, ended up being 9 of them. And then ended up being 6 of the y's. Let's see what's ahead here. I mean, you can almost see what the shortcut is. It's almost like we were doing this power to a power. And once again, we ended up multiplying the powers. But we were also raising this power to this power, which meant, again, you know, we multiplied those powers together to get 6. And we also ended up raising the 2 to the third power because that was also in the bubble. And if you want to get real technical, I mean, you could think of this as not just 2, but 2 to the first power. I'll even write it down, not that you have to. You know, technically you could think of that as 2 to the first power, and so it's almost like you were doing another power to this power and multiply those powers, you know, to get 2 to the third, or just 8. So, anyway, so I guess we have kind of like an official property here. So if you have a bubble of like multiple factors, like something and then maybe even something else, you know, h times k times j, or I don't know, you know, if they're all factors multiplied together in a bubble, and it's being raised to the m power, it's essentially this, where you're raising all the factors to that m power, again, as like a shortcut, right? I mean, you could definitely think of like, or it's definitely not crazy or super complicated to see how you just go right from here to here. You don't need all this nonsense, it's not nonsense, but you don't need all of this. It really could help. Like, if that helps you, fantastic. But it shouldn't be that crazy just to go from here directly to here, because of this whole business. And I don't know if I'm not super crazy about using the word distribute here, but it fits enough, right, I guess. So in other words, it's almost like you're distributing the power, but I'll tell you this right now, it's definitely some foreshadowing, and you won't know what I'm talking about, but you got to really, really, really be careful about when you're allowed to distribute a power like this, because there's going to be certain situations where you're not supposed to just distribute a power to everything in a bubble. Just saying. Okay, here we go. This power, let me get my pen mode. And I always like to go Donatello purple. Anyway, so this power is going to apply to the 3, or if you want to think of it as 3 to the 1st, and it's also going to apply x to the 5th, where that's going to be power to a power for sure. You know, if you think of there being a 1 right here, then both of these are power to a power. But anyway, so it's going to end up being 3 to the 2nd, and then x to the 10th. Okay? And look at the directions. Write your answer in exponential notation. That means I'll just leave this as having a power, and I'll leave it as 3 squared, even though I could easily just make that into what, a 9. 3 to the 2nd power is just 9. But look at, you know, again, the directions said just leave it in exponential form. Exponential notation, I guess. All right, so think there. The 7 is going to be applied or distributed. I think I better like the word applied. So we're going to do x to the 3rd to the 7th. That's going to be a power to a power. We're going to do y to the 7th, or y to the 1st to the 7th. Just y to the 7th. And then z to the 7th to the 7th. Power to a power. We multiply the powers. And that's the final answer. Number 3, not much different. We're going to do x to the 2nd to the 6th. Multiply the powers. Y to the 6th. Or in other words, y to the 1st to the 6th. And then z to the 6th. Or if you prefer, z to the 1st to the 6th. And then it's like officially a power to a power, but and then you multiply the 1 and the 6, I guess. Number 4. Where's my... there it is. So 8 to the 5th, which is probably a giant number. Doesn't matter. We're going to just leave it in exponential notation. And then x to the negative 4th to the 5th. Definitely a power to a power where we multiply those powers. Negative 4 times 5 is negative 20. And just like I mentioned, I think a couple sections ago during the notes, negative powers, I think we're going to learn at the end of the chapter here how we are supposed to handle negative powers, because usually, like as a rule, as a convention, negative powers really aren't good for your final answer. But for now, we'll just leave it like that. Number 5 and number 6. What's with the asterisks? Well, I guess I'll point that out in a second. All right, how do we do 5 to the 2nd times 11 to the 2nd? It's actually sort of a trick question. That's really why the asterisks are there, because in a way it's like a trick question. Because look, the base here, 5, and the base of 11, they're not the same base. So, I mean, to elaborate a little bit more, if you expand, like this was written out the long way, like 5 times 11 times 11, you know, the 11s don't mix with the 5s to make like a larger power. So, really, you know, there's nothing I can do here, really. Especially when the directions said, leave this in exponential notation. I mean, I could make this into 25 times 121, but again, if you're supposed to leave it in exponential notation as per the directions, there's nothing I can do. You know, you can't really do this. Number 6, is it the same situation in number 6? Yeah, because the base 7 and the base 4, they don't match. So you can't add the powers, you know. I guess maybe what might be extra confusing is that the powers match in both of these problems, but who cares? There was never any special rule or special, I don't know, noteworthy thing about that. So anyway, there's really nothing you can do if the bases don't match. So I guess in conclusion, it's all about the bases matching. Now I guess let's move on to a slightly different gear, I guess. Power of a quotient property. Okay? So if you were raising a fraction to a power, whether it was a simple looking fraction or maybe a crazy fraction where the numerator had a lot going on in the numerator and it wasn't just a number or something, or the denominator had a lot going on. If you were raising all of that fraction to a power, that meant that the entire numerator got that power and the entire denominator also got that power. So once again, this like distribute kind of dynamic. Okay, so here's what happens in practice here. And I think we're just going to have these four, I think we're just going to have these four examples. In number 1, the numerator gets that power, and so does the denominator. So we got x to the 5th to the 2nd. That's blatantly a power to a power. And you multiply the powers in that situation. Again, technically, for like the 5th time I'm saying this, you could have thought of this as like a power to a power and just multiplied those powers, but same result. And then we're done. Nothing we can do because the 3 and the x are not the same base. If it was the same base, we could have like subtracted powers, and like done, and which would have meant more simplifying possible, but nope. Number 2, again, this numerator gets raised to the 7th power, so does the denominator, and both of those things end up having, a blatant power to a power situation, and so we multiply the powers. We multiply 3 times 7, and then we do 7 times 7. And x and y aren't the same base, so we're done. On the bottom, now, just slightly more complicated, I guess. So, we're taking it up a notch slightly. In order to raise this entire numerator to the 6th power, it's like this x squared gets raised, but so does the y. Or if you want to think of it as y to the 1st. But it's going to be power to a power. And so we multiply, and then y to the 6th, or y to the 1st to the 6th. Either way. And then don't forget about the z also gets raised to the 6th. Let's do that just for a little bit of style. And then can we do any simplifying? No, because it's like there's x's, there's y's, and there's z's. Nothing's going to cancel out, or we don't have any common bases, top or to bottom. So it wouldn't be like subtracting any powers, And these multiplied together wouldn't mix either, would they? X's times y's? Can't really simplify that. So we're done. And then, there's that little asterisk right there, which means something is afoot. Something might be a little tricksy. And the thing is, can we do 4 to the 6th over x to the 6th, like just because the powers match? Can we do any simplifying? No, because it's a bunch of 4's up here and a bunch of x's down here. There's no simplifying, so there is no simplifying to do. There's really nothing to do, especially when you're supposed to leave this as 4 to the 6th power and not evaluate it, to be whatever it is. I don't even know. And that's another section in the books, 1.8.